Hey, this is Don from Padlock Technologies again with a follow-up video to the VPC configuration video that I did yesterday. I'll put a tag somewhere up here somewhere about VPC from a theoretical standpoint, so you got some background information before we dive into the configuration side, because without that theory, configuration doesn't make any sense, right? You might be able to configure it, but when something goes wrong, you will not know how to troubleshoot it because you don't know how it works from a theory perspective. So what we got here from a basic setup is we're going to do VPC. As you can see, I have a line that has layer 2, layer 3, because in a true traditional build or a correct design, this would be either a collapse core or a aggregate distribution layer switch. And if you don't know about layer 2 to layer 3, you really want to stop the demarcation point between layer 2 and layer 3 is going to be at the distribution slash aggregation layer, right? So in here, we're going to run HSRP, right? We're going to run HSRP for the downstream switch, which is this switch here, right? And then we have some routing going on. Now I'm doing OSPF, and these are ISRVs. So we're going to port channel to each VPC. You're going to see how that works. And then I'm doing the default information originate now on router 3, which is ISRv3. I'm doing the metric type 1, which is going to be basically a, E1 route, if you want to call it that. And then we have on 4 is going to be an E2 route, or just going to be normal default information originate. And when you do that, that's just a normal E2 route, right? And if you know OSPF route selection, you know it's intra, inter, E1, E2, N1, N2s. Okay. So if you're studying for your OSPF or you're just studying for your CCIE, it's very important that you know OSPF path selection compared to, and you need to also know BGP path selection as well. But OSPF path selection, like I said, was intra, inter, E1, E2, N1, N2s. And N1 and N2s are basically not so stubby area redistributed routes. So just make sure you know that. So that is overarching overview of the design. As you can see, we have a peer key live that I'm using the management port for, that by default that is in the management VRF. When you see the VPC configuration, you won't see VRF management, because like I said in the theory video, if you do VRF management is by default for the VPC peer link. The only way you're going to see the VRF is if you use a separate VRF just for VPC peer link. So you might create a VRF called VRF peer link, literally, and then you put an interface in the VRF peer link, in the VRF peer link VRF, and then you would do your configuration based on that. Then you see ETH 3 and 4. That is going to be a port channel, and that is going to be my peer link. So a lot of synchronization goes over that peer link. There are some certain forwarding rules, like if things go over the peer link and you have member ports, it'll be blocked, because nothing really should be going over your VCP peer link unless you have something downstream that's, blocked or port disabled or something like that. Also, you'll see some optimization strategies, because doing VCP, just normal VPC, there was some issues when it first came out, so they came up with some enhancements. I will go over each command in those enhancements. So now you'll see exactly how to do VPC. Now, again, where you'll see this design at, for the most part, is always usually going to be in a data center. You'll see this will be the collapse core design or aggregate, or you will see this in a cross fabric design. If you're doing something like NPBGP VPN from scratch, you'll see VPCs at the bottom for the leaf switches, and then obviously those will be connected to its respective spine. So let's get into this and let's go through the configuration. So we are going to start with the access switch. I only have VLAN 10 on here. Let's see what we got here. Oh, I got to relaunch this. Of course, Apple, why do you always want to give me updates at the last minute? All right, so that's there. Let's reopen this. So from a port channel perspective, if we do show ether channel summary, you will see we have a port channel, and this is where the multi-chassis link aggregation groups come from, because we have a single port channel going to two different chassis from the downstream switch, right? So from an L2 perspective, like if we do show MAC address table VLAN 10, you will see a bunch of Macs here. You'll see a lot of stuff coming from the VPCs. You'll see the two access ports that are going to these two machines there. But now, if we look at from a spanning tree perspective, let me show spanning VLAN 10, you will see that the bridge ID will technically be the same from the VPC, and this is with a certain command called peer switch. That will change the BPDUs, which is the bridge protocol data units, to match, so that from an L2 framing perspective, we have the load balancing between the switches, right? So this is why I have that yellow box around it, because technically this looks like one box from an L2 perspective. From an L3 perspective, there are some other things that we're going to talk about from an L3 perspective and how that works, right? So as you can see, port channel 1 is the root port going up to the VPC pair there, and it's not saying G01 or G02 because I'm using peer switch, and I'm on the VPC. Both of them are the root primary for all the VLANs, right? So let's take a look from a VPC perspective. Let's jump in here. I'll pull this out. So you're going to see router 1. And let me pull this down because I'm a little bit above. I want to show you from a command set standpoint. So if we're looking at, let's log in here. And VPC is pretty simple to configure, but without understanding the logic, you will get burned when things go wrong. So first thing we do from a show command standpoint, if you do show VPC brief, you're going to see a bunch of stuff there, right? So since this is the primary, it says, the peer adjacency has been formed. Peer keep alive is up and peer is alive, and that's from the peer keep alive link. The peer link is going to be that peer adjacency form. We got a couple things here: configuration, consistency status, success, per VLAN consistency status, success, L2 consistency, success. What that means is what you configured on router switch 1 is the same on switch 2. So if I configured, VLAN 10, 11, 12, there's on the primary, there's VLAN 10, 11, 12 on the secondary. If there was like a 13 on the secondary, you would see some inconsistencies there, and you have to run the show, I think it's show VPC consistency status or something like that. Let me see here. Yeah. Show VPC consistency parameter and what the VPC number is, right? What else do we have here? We have peer gateway. I'm going to talk about that when we talk about the configurations. And let's see, we got virtual peer link. We're not doing that. The virtual peer link is a technique. Technically, it does. You can do this in ACI, is where you can, instead of having this port channel here between to do the peer link, you can actually use the fabric for virtual peer links, right? And there's some QoS stuff that you need to do to get that to work. But if you don't really have an issue with links or port capacity, you can get away with just doing the physical ports. But fabric peer link, basically is what they call it, is the technique of establishing the VCP peer link through the fabric, and ACI does that when you configure VPC. Now, this operational layer 3 peer router is a technique. We'll talk about that when you see the configurations, but to sum that up, um, when you do IGPs or something like that, the TTL value is 1. If it goes over the peer link, it decrements the TTL value because you're going to the peer. And then you can't establish adjacency because if it goes through the peer link for some reason to get there, it's decrementing the value, and the packet gets dropped. So with the layer 3 peer router command, it allows traffic or your multicast packets for your IGPs. It allows it to go through the peer link without decrementing the TTL. So if it's 1, it'll be 1 all the way till it get to the second, and then it'll go again. So it allows that happens so you can establish some adjacencies there. So that's really what you would see on both ends. So if you see brief on this side, and as you can see, this is going to be the secondary there. And you'll see that when you see row priority in the VPC commands. So this is how we know everything is good to go. Now, from a VPC standpoint, pretty much same commands, right? This is all you really need to do under the VPC for to configure VPC. So the commands you're going to configure is VPC domain 1. Every VPC that you configure has to have a domain to it. So that's the main command. And then everything else is the sub commands here. So the peer switch was how I was able to get both switches to look like one switch to the downstream switch from a layer 2 perspective. Row priority 1 makes it the primary. Row priority 2 makes it the secondary. This peer keep alive destination 1111 source 1110 is basically the layer 3 keep alive link that I'm going to use. As you can see, you do not see the VRF management because it's VRF management by default. Peer gateway. Now, peer gateway is a command that allows like you're going to do HSRP, right? And then you'll have this HSRP virtual MAC. So what's going to happen to that MAC address is going to give like a uppercase G, which is the gateway tag, which means if any of the switches in the VPC gets that frame going to that destination MAC, that device is allowed to locally switch out or locally route the packet, right? Doesn't have to send it over to the primary to get routed. I said that in the theory video, which is if router 2 gets it or switch 2 gets it, it can locally switch the packet because again, there's separate control planes. Um, Ultimately, each box has its own respective control plane. So then it will just route it based on whatever it sees in its control plane. Fast conversions is a technique. Basically, if something flaps in the peer link here, the secondary will automatically shut down the SVIs and the member port so everything converges over to the primary. If you don't have this in the past, it would shut down the SVIs before it shuts down the port, and then you have some convergence issues there. But with fast convergence, it allows, hey, the peer something wrong with the peer link, instantly shut down the secondaries, member ports, and SVIs, so everything can go over to the primary. And then IP ARP synchronization just synchronize the ARP table between the primary and the secondary. And then these VCPs are the ones that I created for the member ports here. And then VCP peer link is what you would put under this port channel. So if we look at the port channels here, I think this one is 99 actually. So if you, I should have show, that's too much information for you guys. So run interface PO 99. So here's the VPC peer link, and you see bridge assurance is turned on by default. So this is a simple port channel, trunk port channel. It's LACP based because I don't think PAGP is even a thing on network switches or Nexus OS again. And then the minute you type in this VCP peer link, it puts this spanning tree port type network, which is bridge assurance. And you need to have bridge assurance on your VPC link. Now I'm showing you a bunch of stuff on the primary, but it's pretty much the same on the secondary, right? So now when we're talking about VPCs, I believe this is show run interface port channel 1. So what I'm doing is I'm just sending, and this is port channel 1 is connected to E5. So the key here is if we're looking at E5, you got to do all these things on E5 first. So you do the switch port trunk. I'm only allowing 1 and 10 because I don't want the other VLANs to go down there. Then you say channel group 1 mode active, which is LACP. And then you have to go to the port channel and then give it the VPC1. Same thing over here. So we look at interface PO1, same thing, VPC1. When you do this, this allows the virtual port channel to happen. This allows the downstream switch to look like it's connected to one switch, right? Because the VPC numbers have to match. If they don't match, you're going to run into problems. So we look at our short port channel summary here. As you can see, we have a port channel here, which is a layer 2 because you see the SU here. And then we do here, port channel. Same thing here. So the only 199 is our peer link because you see it says ETH 1 and 1.3 and 1.4, which is the peer link between the two peers, but everything else are member ports in its own respective VPC, right? So port channel 2, I believe, is going to ISR 3, and then port channel 3 is going to ISR 4. And because you see this P, that means it's up. Like you see SU, that means that the port channel is up and running. Now, the difference here is we'll shut this down here, and we're going to go to the ISR routers. And if we look at the show Ether channel summary, we have a bundle, a port bundle, and it's a routed port channel because you see RU. It's a routed port channel because this port channel actually has an IP address assigned to it. Yeah, so you see it has a routed IP assigned to that port channel, so it makes it a routed port channel or a routed link aggregation group, if you want to just call it that as well. And you see the bundling there. Now, same thing on the other end, it'll just use port channel 3. Now, here's the thing about the routing situation. So we're going to open up 1 and 2 again. I want you to see this. From a routing perspective, when we look at our OSPF adjacencies, you will see an adjacency with 2, which is right here, an adjacency with 2, an adjacency with 2 again, an adjacency with 3, an adjacency with 4. Now, this one here, I should have put the priority on this, so this would always be uh, the BDR on the other side, but I didn't do that, so it is what it is. But from a routing perspective, you see all these adjacencies on here, right? And this is because the peer link is carrying all these VLANs, so it's sending that multicast traffic between the peer link. This is why I say from a routing perspective, you got to be careful. Because if you look at IP route OSPF, you will see I can get the 2 from all these different, look, I can get to the 2 from 10.3, which is our 10.253, which is over here, then .2, which is over here, then 12.2, which is over here, right? So sometimes if something should happen, now again, this is really based on as long as nothing happens to the peer link. Let's say if you had the IGRP, right, and you had it not port channeled, but it was just a single connection like this. What would happen is, let's say you can see this router would see, hey, to get to 2, I can go this way, or I can go to router 2 right off the, or switch to right off the bat because I'm connected to it, or I can go through router 1 or switch 1 to get to 2, right? And then whatever routes is learned from 1 can go to 2, and 2 can send it back to the 3. So you can see where this can end up becoming a loop at some point, right? And I've seen that happen where the routing was supposed to go one way and it wasn't going another way because it's seen it as a more preferred route going through the VPC. You don't want to have that. So I suggest if you're going to do VPC, everything that is not a host from a networking perspective should be port channeled up. And that's why I make sure that, you know, router 3 and 4 we're doing a port channel and not doing, point to point connections here, because it can cause routing issues, right? Now, as you can see, I have quad zeros coming from 11.3, which is technically router 3 here. And as you can see, you see that type 1, that means I'm doing a metric type 1 when I do the default originate. And then if we look at our our IP data ROSPF database, you will see from an external standpoint, I'll have two routes, one from 3, one from 4. Obviously, the one I'm getting is from 3, but I'm also getting one from 4 because I'm default originating that one as well. Same thing on this side. Let's just do external for now. So I'm getting one from 1 or from router 3, and then the second one, since it's not a metric type 1, I'm only getting, you know, I'm getting 2, but since the other one's a metric type 1, you're not going to see that in the routing table. So if I show IP route OSPF, as you can see, it is going to 11.3, which is router 3, because it's a metric type 1. And that's how you kind of manipulate external routes via, uh, metric type and stuff like that. So now all the routing is there. So at the end of the day, oh, I didn't show you the MAC address thing. Hold on. Oh, got to show you that. Or did I show you that? Did I do VLAN 10 on this? Okay, here we go. So, see this G here? These G's are technically the MAC address of the SVI and the MAC address of the HSRP MAC address. Right? So, if you look at VLAN 10, you see we have HSRP version 2, 10, we have some authentication we got some authentication going on, minimum delay, stuff like that, right? So we do show HSRP, let's go 10, all right, what is it again? A group 10. All right, so we look at the MAC address, which is this right here, 0000, 0C9F F00A. That's the virtual MAC. So we go back up here, we just see G next to that virtual MAC, which is right here. Okay, so this is right here. So what that G means, if anybody sends a frame destined, or just packet, which is encompassed in the frame and stuff like that, if you know anything about the OSI layer, application data, we'll just say data because data encompasses application presentation session. Then you have your transport layer, which is your segment, which goes into a packet, which goes into a frame, which goes to the wire, right? So if you're going to send, if you know anything about, this is the layer 2 rewrite. So if you're not on the same network, like if you do the anding process and you realize, hey, well, I'm not on the same network, I need to send it to my default gateway. So you do a layer 2 rewrite instead of sending it to the MAC, because you don't know the MAC address yet. So you're going to send it to the MAC address of your default gateway. That's the layer 2 rewrite. So what would happen is if I'm trying to go to another network, I'm going to do the process, realize we're not on the same network, and then I'm going to send it to this MAC address. So what this G says is if you send it to the MAC address and you just happen to go over to switch 2, switch 2 is allowed to locally route the packet. So this is why I'm saying 2 different control planes, right? Because you saw from a routing perspective, I didn't just do show IP route and that was the routing table for both boxes. It was that show IP route is for that single peer. So if it went over to switch 2, it would have to see some routing in there to route the packet out, because as soon as you see that G on there, it's telling the switch, hey, you can locally route this packet on your own based on your own routing table. This is why you need to make sure things are dual homed, or you actually have a way out on the secondary switch. Because if you only have the stuff going on the primary switch and the secondary switch answers it, you could potentially black hole traffic. That's why you have to make sure the routing works on both ends. But because of this G, if I were to send, a piece of, if I do a ping and let's say it go up to the access switch, goes to switch two, well, switch two is going to say, do I have a way to get out? If the answer is yes, I'm going to route it out that way. If the answer is no, it could end up dropping the packet because you don't have anywhere to go. Didn't want to miss out of showing you that. So now let's test and see if we can ping out to the internet. Now I'm doing just a static, a basic NAT here. So we should be able to ping out to the internet here. So we'll ping 1.1.1. And as you can see, we are pinging to the internet perfectly fine. So now let's see if we trace, hopefully trace route works on this VPC here. I just want to see how far, yeah, I think it's trace. Yeah. So as you can see, we went to 192, 168, 252, which is switch one. Then we went to router 3. Then we just went out of my network, and then once we got out of my network, it went to 1.1.1.1. But as you can see on this trace route, it's always going to go there because technically from an HSRP perspective, primary should answer it. But again, once I get the frame and I send it to at the frame level, if it goes to router 2 for some odd reason, not router 2, it goes to switch 2 for some odd reason, switch 2 could technically route it. So that was VPC in a nutshell. We went over the configuration, went over the design, went over the routing, some gotchas. We went over VPC enhancements, which was the peer switch, peer gateway, IP ARP synchronization, fast convergence, layer 3 peer routing. Rewatch this video if you didn't catch it the first time, but we went over everything from a VPC perspective. This is not the only way to do VPC. I told you before, you can do back-to-back VPC, which is VPC connected to another VPC, right? So you can do that as well, but you need to know how to do the basics of VPC that's in this video before you even try to tackle VPC, back-to-back VPC, right? And this will definitely help you if you're getting into learning how to do, MPBGV with the VXLAN and all that good stuff. You really need to know this because 9 times out of 10, you're going to have to configure VPC. And there is a gotcha when you configure VPC with MPBGP EVPN. There's an order of operations that if you do not do the order of operations correctly, the VPC will not come up. So this is Don from Padlock Technologies again. Hope this video was informative. You got any questions from a technical perspective? I don't know everything. I know a lot, but I know everything. So if you got a question, it's going to be a video bumper at the end where you can send your questions. Hope this video was informative. Thank you and have a nice day.